Welcome to the explainer on Bayesian alternative to regression. So as usual, I ask you questions, and if you can, pause the video, go to the masterclass and try to answer these questions, and then return to this video to see my answers. So, first question, what is the most important philosophical difference between causal models and linear models? And the philosophical difference between these two models is that one type of models, the causal models, are models about reality. They make a claim about things that happen in reality. And they have some certain degree of abstraction. It's not a mechanical model, so it doesn't tell all the components in nature and that form part of a mechanism. These are more complex models, but so they have some abstraction, which is to divide the world into variables and making connections, causal connections or links between those variables. But it's still a model about how things are and are modified and how they change in reality. Whereas the linear models they belong to probability, and they are models about numbers. So it's a way of combining numbers and getting numbers. So we can put a name to the variables that are used in probability, but we always end up with numbers or values. So this is the difference. A linear model cannot make any claim about reality. It can make claims about numbers, about mathematics. So can we use probability models or linear models to explain reality? No. But are they useful? Extremely useful. They are useful. Combining the causal models with the linear models, we can make a claim about reality. The causal model tells us how two variables are linked and which variable causes the other variable, but we don't know about the strength of that link. And the mathematical models can help us to understand the strength of that link between variables. One variable can I can change one variable and causes a change in another variable, but the change could be minimal. There is a causal relationship, but it's a very small change. And in order to know about that change, we need the linear models, or any other mathematical model, but we are using here linear models. So this is the important philosophical difference, that you won't find this differentiation in psychology research, unfortunately. And you will find the linear models or other type of models, probability models, as sort of explanations of reality, but they are not good explanations. So in those explanations, because we cannot establish causality, sometimes there is the researchers give up and they don't make claims about causality, because the linear models cannot say anything about causal relationships. So these are the main differences, philosophical, between these type of models. Second question. Provide examples of perfectly reasonable linear models that cannot be causal models. And my question also, the follow-up question is, those linear models that cannot be causal models are useful? If they cannot be causal, are they useful? Okay. Okay, so here I'm giving some examples, but I want to answer the second question. Even though linear models may not be causal models, sorry, they are not, but also there is no direct translation, they can still be useful, very useful. We can make predictions about things that will happen, but we don't have a clue what causes what. We can make predictions based on one variable, what is more likely to happen, or what is more likely to observe in another variable, but without making any causal claim. This is still useful and is fine. And some researchers they say that that's what science is about. But other researchers want to know about the causal links between variables, then they want more. Now, what we need to do is when we use the linear models without a causal model, we shouldn't make a causal claim. That's the real problem. Okay, so I give you examples. Some I provided in the masterclass, but some are new. So, first example, practice is a causal variable and age consequence variable. So practice changes age. The linear model is as usual. Y is normally distributed with gamma as mean and sigma as standard deviation, and then gamma equals beta 0 plus beta 1 times x, and where x is age and y is age and x is practice. So that's the linear model, and the translation of this linear model into the causal model is that practice changes age. No, this is not possible. Why? Because age cannot be changed by practice. So we cannot make causal claims where there is it's impossible. Okay, so no matter how we practice something, we cannot change the age. So second element, the second model, the opposite, age changes practice. Well, this is not as bad as the other one, but the idea is that age is, if we consider age as a proxy of something else, then that's fine. But age in itself doesn't change a behavior. It may be the case that the older you are, the more you practice, or the more practice you accumulate. But it's not the age what causes that. It is the maturity of people, the capacity to engage in more hours of practice. That explains, that is causing the practice. So age is not the causal agent, so it couldn't be a causal model. It's not as bad as the other one. Some people may use this because age is a proxy for these other things, but we should try to avoid this type of causal model. But as a linear model, no problem whatsoever. We can try to predict practice based on age. Both things are okay. Predicting age based on practice or predicting practice based on age. These are legitimate research questions. Third example, gender causes changes in verbal skill. Well, so for example, here we know that female tend to be better than male in verbal skills. So is this not gender having a causal relationship with verbal skill? Well, this is the same issue as age. Gender is a proxy for something else. It's perhaps a different interest. Perhaps female have more interest in verbal material than male. perhaps they spend more time reading or writing than male, or perhaps there is some aspect in their brains that makes them better at verbal skills. This is similar to age. Gender is a proxy for something else. Now, if we are not interested in a causal relationship, the linear model is perfectly okay. We want to know differences between genders in verbal skills is legitimate and it may be useful, but it's not a causal model. Similar, gender is verbal skill, or if we put in sports performance or in sports of strength, then male would be better than female, but it's not gender. Is the muscular the strength that produces the performance. So why is that differentiation important? For example, you can if you're a female and you develop muscular strength, then your performance will improve. And so it's not a gender, but it's the muscular mass. So another example of this type is a country of birth changes, modifies sport achievement. So you can study differences between countries in sport achievement, and it's a clear difference. We've got some countries that have a much more important achievements than others. And in itself, as a linear model, that's perfectly okay. It is useful for making decisions, etc. But is it a causal model? Is being born in one country is the cause of different differences in sport achievements? Well, no. It is perhaps the infrastructure that you have in this country that is the cause. That is what makes the difference. The country of birth is a label, but could be the infrastructure, could be the culture. One culture may be more encourage people to do sports and others less. But is that the encouragement that people receive to engage in sports? That is the cause, and that may be different in countries. So again, country of birth is a proxy for these other things, but as a causal model is not a good one. Okay, let's move to another question. What is the difference between simple regression and multiple regression? Okay, the answer to this question is simple. In simple regression, we've got one independent variable and one dependent variable. Another way of calling this independent variable and dependent variable in regression is the independent variable is called predictor variable and the dependent variable is called outcome variable. So these are different ways of referring to these variables, and comes from different disciplines use the different terms, but they are the same thing. So the difference is that in simple regression we've got one and one. One dependent variable, one independent variable, both are numerical. So typically continuous or they are discrete, but with a large range of possible values, not with a small range of values. And multiple regression has two or more of the independent variables. So in both cases is one dependent variable, but in simple regression is only one independent variable. In multiple regression you've got two or more independent variables. What is the main effect of using mean-centered variables in linear models? Okay. In the traditional approach in linear models, we use the raw values as variables so the raw values of the independent variables as variables. But in when the models become more complex, is useful to use mean-centered variables. It may not affect much when we use two variables, but when we start using more variables, it will affect, and more complex analysis that will come later in the unit will see that this is essential. And what's the main linear model with raw values? And this one is when the values are mean-centered. And here I'm showing you only one independent variable. So national rating is the dependent variable and only one independent variable. But this model shows the two variables, so this is a multiple regression. So for the null model, the mean will be the beta 0 is the mean of y of national rating, and then beta 1 and beta 2 will be 0. So that's why you've got a straight line, a horizontal line located in the mean of y. So in the model that is it incorporates two variables, two independent variables, in this case group practice and individual practice. Then we've got a line, and of course this is not what that model is, because when you have two variables, instead of having a line, we have a plane. So I need to add a third variable and use a perspective to resemble 3 dimensions. But I don't want to do that, because if I add a fourth variable, now it's impossible to visualize. So let's just stay with this visualization of two variables, which is intuitive, and then the rest we analyze intuitively, not with graphs. So here we've got the intercept on 1853, which is where 0, this is 0 for x, and for y is 1853. And then you've got the slope, which will be different than this in here, because you need to take into account both variables. Now, what changes with mean-centered is when you mean-centered, what happens is that the mean of that variable becomes 0. So when you mean-centered, what you do is to subtract the mean from all the raw values. So if you've got if the mean is 100 and the value of one value is 50, then you do 50 minus 100, negative 50, and that's the new value. What does it mean, negative 50? It means that it's 50 points from the mean, and it is a lower value than the mean. The negative sign tells me that it's a lower value. And if another value is 200 and the mean is 100, so 200 minus 100, the new value is 100. The mean centered value is 100. It means that it's 100 points from the mean, and that is a higher value than the mean because it's a positive number. So when you now take the new variable, the mean center variable, the mean of those values is 0. Okay, and that's what we have in here. So now the mean of the variable, the mean is 0, and is indicated by this line. And if you continue this line, this would be the mean of a total group in this graph. So what happens is that now the slope of the regression line will intersect always here. So the slope could be lower, but it will intersect there. It could be more pronounced slope, but it always will go through here. So basically now the beta 0 will be the same as in the null model. So that's why we have here, we've got the intercept is 1853, and the beta 1 0.017 and the beta 2 0.062, whereas in here is 1988, which is exactly the same value as the mean of the beta 0 in the null model, and the beta 1 and beta 2 remains the same. Okay, next question. What Bayesian method shall we use for Bayesian regression? The answer is simple: Bayes factors. We use Bayes factor to compare models, and we determine which model, we provide the evidence in favor of the models. We remember, we don't have to make a decision. If we have to make a decision, we make it, but if we don't have to, we just report the evidence. What does it say? And we quantify the evidence with the Bayes factor. Another question: what is the difference between the posterior distribution of the parameter values and the posterior distribution of the models? Okay, these are two important important components of the Bayesian approach. The posterior distribution of parameter values, it gives us a distribution of the beliefs that we have after observing the data of what are the most probable parameter values. Parameter values, I mean beta 1 and beta 2. And the posterior distribution of the models is the credence that we have after observing the data, the credence, that we give to each of the models. So we have a model of the null that says that there is no effect. These two variables don't make any change. They are not good predictors of the dependent variable. We've got a model that says that one of the variables predicts well, but not the other. In the other model, the other variable predicts, but not the first one. And in another model, the two variables are good predictors. So we've got four models. We start with a prior distribution to the models, and a typical way of doing that is just to provide the same value, the same possibility to each model. We say, well, we don't have any idea, and so we give the same probability to each model. But if we have reasons to believe, we have previous studies that they tested these models and they came up with the posterior distribution, we can use that posterior distribution of that study to inform our prior distribution. Excuse me. So in the posterior distribution of parameter values, we use a Bayes theorem in which it has the parameters data form. So the posterior of the parameters is what's the probability for the possible values of the parameter theta given the data we observed and in model 0. And we do that with model G, which is, that says in this case that the good group practice is a good predictor. We do the same with MI, that individual practice is a good predictor, and MGI is the model that says that both variables are good predictors. And this is the theorem that we've been seeing before. The only difference is that it adds the comma M0 in or given M0 in all the components. And basically we are saying if M0 is true, what are the probability of all these parameter values and the data? Okay, and the form is the same for each model. What is different is the priors that we give to the parameter values. So the priors that we give to beta 1 in model 0 is that value is 0. So all the probability is given to 0 and nothing to other values. In MG, we create a distribution around 0, but we give some credence to values more than 0 and less than 0. And in this one, in MI, for the beta 1, 0, because we say that this variable is not important. And for MGI, the same probability distribution as in MG. So that is different in the models, the prior. This the probability of the data given given the parameter values. That's the sampling distribution. That's what we saw in many other analyses before, and that doesn't change. It's the same distribution for all the cases, and typically we use a T distribution. And the probability of the data for each of the models, it's a sum. Remember that probability of the data here in the numerator is always a sum. If we are talking about continuous variables, it's an integral, not a sum. But an integral is like a sum. Sum of what? Well, of all these. This one is for all possible parameter values. So if we have a parameter 1, parameter theta can be, let's say theta could be 1, 2, and 3. Okay, if theta is 1, then we do this calculation. If theta is 2, it's a different calculation. If theta is 3, it's a different calculation. So we do all these calculations and we add these 3 values, and that is this value. Okay, so that's the probability of the data for each of the models. Now, this probability of the data for the model we are going to use in the different version of the Bayes factor, which is the version of the models. So this is the models version, and remember I said we are going to use the probability of the data given the model, and this is this value here. So the Bayes factor has the same shape, the same form as the parameter and data version, but instead of parameters we've got model. And this prior here is the probability we give to the models, and we said that we are going to give the same probability. So if we have 4 models, these have to be 0.25, 0.25, 0.25, 0.25. Probability of the data is probability of the data averaged over the 4 models. Over the 4 models. So it's exactly the same value. So if this PM0 or the prior for all the models is 0.25, which is the same value, and this one is the same value for all the models, when we compare the models, we can eliminate these 2 values. And if we eliminate these 2 values, then we have this equality. Probability of model given data equals probability of the data given the model. So when we have this value that we have from the other form of the Bayes theorem, then we that's equivalent or equal to the posterior for the model. Okay, so and then the odds version of Bayes theorem is we compare the theorem for a model with the theorem for another model, and so that's what we have. For example, here we are comparing the null model with the group model. So what's the probability of the model after observing the data? What's the probability of this model after observing the data? And that equals the probability of the data given the model because of the what I indicated before. So these values we can calculate from the combination of functions that we use for the prior, for the sampling distribution, and then we come up with that value. And then when we do this ratio, this is the Bayes factor. This is base factor of 0, 1 because we've got the null model on top compared to the other models in the 3 cases.